we're going to go over an example of a dynamic programming problem, or rather a class of dynamic programming problems. And these are ones having to do with range sum. Now, you might remember that we've already encountered range sums. In fact, this was the whole thing that we used to motivate Fenwick trees, and it's one of the things that we can use segment trees for. And the difference is Fenwick trees and segment trees are great if you're going to update the data in an array. And so if you just sort of remember the basic idea here is you've got some array of values and you want to be able to find what's the sum over some range in that array and calculate that quickly. And we talked about how you can do that with segment trees and with Fenwick trees. Now, if you're going to keep updating values in this array, at all frequently, it's better to use a Fenwick tree or a segment tree to do that. However, if the data stays static and you're just going to run a bunch of queries on the data, then we can use a different structure. And the basic idea is something called a prefix sum, although there's a lot of different variations on it. So I'm going to go over and show you how prefix sum is done in this case, but the principle will apply to some other things as well. Now, keep in mind that when you are doing this, the whole motivation here is that we read in the data one time and we perform a lot of queries. If we only have to do one range sum, if we're only doing one sum, then just make a loop and loop through all the indices and sum them up. There's no reason to use anything fancier if you're only going to perform one query. But if you're going to perform a lot of queries, then we can use this prefix sum idea. So the idea of performing a lot of queries, and the reason why this falls into a dynamic programming approach, is you end up solving the same subproblem several times. So just without putting any numbers in, let me just illustrate it by drawing this, by drawing some array and showing you what I mean here. If I've got elements, and I'll write the indices down here at the bottom, 0 to 7, and I want to calculate, what is the range from 2 through 6? Well, I'm going to be adding up 2 plus 3 plus 4 plus 5 plus 6, and actually I'm going to be adding up the values in each of those indices. If I instead have something that, say, is 0 to 5, then I end up adding 0 plus 2 plus 0 plus 1 plus 2 plus 3 plus 4 plus 5. And if I end up adding up something like, I don't know, 3 to 5, I end up doing 3 plus 4 plus 5. And you can see that in all of these cases, several of the elements here, in fact, in all three of them, the elements 3, 4, and 5, that sum is going to appear in all of them. And in fact, in the first two, you're also going to have this 2 that appears in both of those. So if you're going to perform a lot of these range queries, you're going to end up basically wanting that sum multiple times. And so you have the same subproblem that you would keep solving over and over. Now, the way we can deal with that is we can compute the prefix sum. And the prefix sum is going to just give you the sum of all of the elements up to a particular point. So it's going to give us the sum over this range. And notice now, if we have, in this case, it might be 0 to 4. If we have the range from 0 to 4, and we have, say, the range from 0 to 1, okay, if we have this range, so we know that value and we know this value. If we know those two sums, well, if we wanted to find the range from 2 to 4, we would just subtract one from the other. And so if at every element we have the sum of everything up to that point, well, then we can compute a range sum is just going to be 2 lookups and 1 subtraction. And that's it. So we can actually perform then a range sum after we've pre-computed things. Every time that we want to actually sum up everything in a range, that's a U, we can do that with just 2 lookups and a single subtraction. So let's look at an example of this. It's not really very complicated at all. So let's create an array here. 1, 2, 3. Okay, so I guess that has 12 elements, and I'll just number them. I'll write the indices down here. And let's say that we're going to put values inside of each of these, and we'll just come up with some values like 3, maybe -2, 5, -1, 7. Let's do something really negative like -20, 3, 8, I don't know, -4, 6. Let's say -9, 1, something like that. Okay, so we've got a bunch of values there. We've just written them all out, and we want to be able to compute what the values are across any subrange of these elements. So if I'm going to do my prefix sum, so this is going to be the prefix sum, and the reason it's called the prefix sum is you're summing the prefix. So everything from the first part of the array all the way up to your point. So if I'm going to compute the prefix sum, I'll write that in blue down here. Well, the first element is 3. And then you just add on the next element to what's there. So 3 plus -2 is 1, plus 5 is 6, plus -1 is 5, plus 7 is 12, -20 is -8, plus 3 is -5, plus 8 is 3. -4 would be 4. Sorry, wrong. 3 minus 4 is -1. Plus 6 is 5. -9 would be -4. Plus 1 would be -3. Okay, so there we've computed the prefix sum. And so now, if I were to ask you, what is the sum from elements, I don't know, I'll just say 3 through 9. Okay, what I can do is I can take the value at 9, and if I look at the value at 9, that's the 5, and I'm going to subtract off the value at 2, 1 less than 3, and the value at 2 is 6, and so 5 minus 6 equals -1. Okay, and it should be that if I actually sum up the elements from 3 to 9, I should get -1. So -1 plus 7 is 6, -20 is -14, plus 3 is -11, plus 8 is -3, -4 is -7, plus 6 is -1. And so in fact, the sum is -1, just like it should be. Okay, and we can do this then once we've done this one pre-computation, and notice that it's just an order n computation to do this. We just run through the array one time. Once we have that, we can sum up everything else very quickly. Or we can find these range sums very quickly. Now, there's a variation on this that we can do. We can do something called the max range sum. Okay, so the idea of the max range sum is that we want to find the maximum over any subrange. Okay, and this might seem like a problem that, well, it's just too complicated. I mean, we could try, well, what is it from 0 to 11, 1 to 11, 2 to 11, 3 to 11, 4 to 11, blah, blah, blah. And then what is it from 0 to 10, 1 to 10, 2 to 10? And we'd end up with n squared checks that we'd have to do. And that's way too much work. We can't do n squared checks. That would often take too long. However, we can actually make use of a small variation on the prefix sum to compute the max range sum. And it's the same principle that we had before, where we're going to use the values up to a point. But there's one key difference. So with max range sum, the idea is anytime we encounter a sum that is less than 0, then we want to reset to 0. And here's the principle of what that means. What that means is if I ever come up on a particular point and I want to be able to calculate the maximum sum up to that point, if I ever find a point where the sum is 0 or less than 0, so like let's look at this number right here, -8. Okay, that means that if I sum up everything up to that point, I got a negative value. That's going to be the first negative value that I see. If I'm going to take any sum after that, there is no reason I would ever want to go earlier than this point, because I know that the sum of anything that includes element 5 and before, if it includes element 5 and anything before, it's going to be a negative value. I know that that's the case for sure. So I would never want to use that if my sum is one of the later values. I'd never want to use anything from 5 or before. And so I would, instead of making my sum -8, like you see down here, at this point in the max range sum, I would reset things to 0. So let's look and see what the values here would be for the max range sum. I'm going to pause for a second and just copy this array down below so that we can see it fresh. Okay, so here's the array, the same array that we had before, but now I'm going to do the max range sum, and I'm going to say what's the maximum sum that I could get as I go along through this array. So first of all, this would sum up to 3. 3 plus -2 is 1. 1 plus 5 is 6. 6 minus 1 is 5. 5 plus 7 is 12. Now 12 minus 20, that's going to give me a negative number. And so instead of putting in -8 here, I'm just going to reset this to 0. And again, what this means is from this point on, the best I can do from this point going forward is something that has a sum of 0 before it. It means basically I want to ignore everything from element 5 and earlier. Okay, so now I start over with my sum again, and I get 3, and I get 11. And here I would get 7, then I would get 13, and then I would get -9 is 4, and this would be 5. Now, if I look through this whole thing, I would see that the maximum sum I can get is 13. That's the highest value that I got along the way. And so what that means is I can take the sum, and in this case, I'll just mark it here. It would be the sum from that element back to wherever the last 0 was. That range is going to sum up to 13, and that's the largest value that I had anywhere. Notice the next largest value I had was 12. That was over here, and that 12 would be from there up until the previous 0, which was all the way back at the beginning. Okay, you can think of this as starting out with a sum of 0 way back there. Okay, so that will be able to tell me what the maximum range sum I have over these regions is. In this case, it was 13. If you want to, instead of like linearly searching for the last 0, you could keep track of the last thing that you saw that was a 0 along the way. For instance, I could keep track of the last 0 I saw here was -1, and -1, and -1, and -1, and -1. And here I hit 5, and so I stay at 5 the whole way through. Like that. And if I wanted to extend this array a little bit more, just to kind of illustrate, I have something like -8, and I have 4, and I have 3. Okay. We'll notice here, if I were to have continued this out, 5 minus 8, I would have to reset this to 0 again. Then I would have a sum of 4 and of 7. And the previous 0 that I saw now would be at element 12 for all of these. Okay. So that if I ended up with a much larger value, just to be even more, let's say this was 100. Well, now I get 107, and that's going to be the largest value, and so it's going to be whatever this index is, 12, 13, 14, 15. It would be from number 15 back to number 12. That was the last time I saw a 0. Okay, so or that was the last 0, so I could actually go one more than that. It would be to number 13. Okay, so that's the idea of the max range sum. It's again just a slight variation on the range sum problem, and it will keep track of the maximum. The max range, most people can understand the range sum, okay, if you just think a little bit. Max range sum is sometimes a little bit trickier, but remember the whole idea is you reset it to 0, since from that point before that, there's no sense in keeping any of that. There's no possible way that anything from that point earlier could give you a larger sum than just ignoring the stuff earlier. Okay, so there's one other range sum problem that I just want to show you to illustrate. And it's a problem I've actually run into something like this in research before. And the idea here is, what if you have a range sum over multiple dimensions. So it could be 2 or 3 or something higher than that. And so the way this will work is if you have a grid of values now, okay, like here I'll do a relatively simple grid of values, just something that's 4 by 4. And there's going to be some, value in each of these elements. So I'm going to pick something. Okay, so there we go. There's a bunch of values. And if I want to, instead of what I had before was I was, just taking a one-dimensional range sum. So I had an array and I was saying starting point to ending point. And so I would get the sum up to there, and then I would subtract off that part. The question is, how do I do that if I've got something that's in 2D? Is there a way to modify this for 2D so that I can make a query such as, what is the sum of everything over some region, like the part that's outlined in blue there? And there actually is a way to do this, and it's just a variation on the prefix sum that we saw before. The idea is in every element of our, it's weird to call it a prefix sum, but in every element of our sort of block prefix sum, we are going to sum up, if this is the element, we're going to sum up everything in the entire region that is to the left and below that element, including the element itself. Okay, so for this first one, it's just the element 3. For this one up here, right above it, it would be 11 because you have an 8 and a 3. For this one over here, it would be 4. For this one over here, it would be, it would be 4 plus 9, so this would come out to be 13. Okay, and we can do this over the entire chart. So I'm going to do this just for a minute so that we can figure it out. That's 8 and that's 13. And we can go up this way. 3 plus 11, or 3 plus 8 is 11. 11 plus 2 is 13. 13 plus 1 is 14. So if that was 13 plus 3, this is 16. And then we add, I believe that comes out to be 20. Okay, and so if this one was 13, okay, I'm going to just jump ahead here. Okay, so this is the sum table filled in. And again, remember, every element in this table has the sum of everything that is to the left and below it. So the cell in the upper right, that's the one that's up here that's labeled 46. That means that the sum of all of the elements in this table are 46. And so now, if I want to find the value for a particular block, such as this, such as the one that's outlined in blue, and this is a little bit tricky, so watch carefully what I'm doing. What I'm going to do is I'm going to first start off by finding the sum of the entire area, which is this area here. Okay, so I get that entire sum. And then I am going to subtract off this region there, and I'm going to subtract off this region there. So in other words, I'm going to take the one in blue and I'm going to subtract off that one and that one, because notice that they happen to both be 13 in this case. This 13 up here, that's the sum of these three values, 2 plus 8 plus 3, that sums up to 13. This 13 down here is the sum of the values along the bottom row, 3 plus 1 plus 4 plus 5, that also sums to 13. And so if I take the first number, 39, that's going to be the sum of everything in this little block down here, and I've took off those two blocks, but you might notice one thing. There's one value here that got subtracted off twice. It got subtracted off in both the red areas. And if this table went on, if this was not just ending there might have been an entire block here of additional values that also got subtracted off. Okay, so what we end up doing is you would take the blue value and you would subtract off the two red values, and then you would add back in the green value. Okay, so in this case, if I wanted the sum over that block there, what I'm going to do is I'm going to take 39 minus 13 minus 13, and then plus 3. And so if I do that here, what I end up getting is 39 minus 26 is 13. Oh, and I'm sorry, then that's plus 3. And so 13 plus 3 should be 16. So if I did that correctly, if I sum this up, 7 and 1 is 8. 8 plus 2 is 10. 10 plus 4 is 16. Plus 1 plus 1 is 14. Plus 2 is 16. Okay, so indeed that blue box did sum up to 16. And notice I could do this for anything that I wanted to in 2D. In this case, I can just take my upper right corner and I can subtract off 2 other corners and add back in the fourth corner to sort of counteract the extra stuff that was missing and get that. And this idea extends up into an arbitrary number of dimensions. In fact, I told you that I used something very, very close to this in a research project. And in that case, everything was in 3D. So basically, I built this big table in 3D and just took one corner and subtracted off 2 others and then added, or sorry, I took one corner and to subtract off others, and then you add some back in and you subtract off, and you sort of alternate this adding and subtracting depending on the number of dimensions. But the basic principle is exactly the same as what we had in the original prefix sum. This just happens to be a 2D version of it. And I think it's actually a pretty cool problem. Okay, so that is the idea of range sum. And again, the whole reason that this falls into the dynamic programming set of problems is because you end up, if you do multiple queries like this, you end up creating the same sums over and over. So you have the same subproblem that you have to keep solving over and over and over. And so by just computing it one time, sort of pre-computing some of that data, you don't have to recompute it over and over and over again.